Hello, this is Jack Jackson. In this playlist, we're looking at the mathematics of the 18th century. We started the playlist by kind of giving an overview of some of the mathematical advancements in this 18th century. We're going to continue in this one here by looking a little more detail at some of the advancements. So first of all, I'll talk a little bit about mathematics education. So mathematics actually was not that emphasized in many universities of the time. And so a lot of the most prominent mathematicians didn't work in universities, but rather they worked in academies that were supported by various royal patrons that became centers of mathematical advancement and education. Particularly kings of a particular country might have an academy set up to, they might have a military academy, they might have academy to set up to train. Of course, military would be to train their military leaders. They might also have one set up for engineers and scientists. They might have another one set up for training teachers. In particular, in France, École Polytechnique was set up to be technical education, including advanced mathematics, an engineering school. École Normale was training of teachers in France. So these were two uh, schools that were put together in the later part of the 18th century, and the top mathematicians of the French Revolutionary period taught at these schools, or perhaps at the École Militaire, military school. And these mathematicians were developing the curriculum for these schools as well. So let's kind of take this kind of one subject at a time, or one subfield of mathematics. Let's start with calculus. A lot of what was going on in the 18th century was around calculus. Remember, calculus had just been created in the last few decades of the previous century, and really the entire 18th century, a lot of mathematical endeavor was focused on developing calculus. So there were expansions of the techniques of calculus and their applications to science. For example, additional integration and differentiation formulas were added in. Trigonometric functions now were lifted up to the same level as other functions. Trigonometry had been used for many years to study astronomy, for example, and to do some other technical building type things. But trigonometric functions were now lifted up just like, say, algebraic functions or exponential functions as things that you could do calculus with, find the derivatives and antiderivatives and do integrals and so forth. Logarithms were also something that were studied quite a bit, and extensions of logarithms, like logarithms of negative numbers and so forth, help lead to understanding a little bit more about complex numbers. Differential equations started showing up, arising from many physical problems, and so calculus techniques were determined to derive those differential equations and to solve them. Infinite series became used to solve some integration problems. A couple of extensions, calculus of variations, which involves minimizing or maximizing a particular integral. Multivariable calculus started to grow in that century as well. Things like partial derivatives and multiple integration came. Some of the key mathematicians in this growth of calculus we've already talked about: Leibniz, various members of the Bernoulli family, D'Alembert, and probably the biggest one of all, Euler, did the most to advance calculus in this century. There were several important calculus texts that were written. L'Hôpital wrote the first one. We now know that a lot of it was based on the lecture notes of Bernoulli. That's Johann Bernoulli. Thomas Simpson in England wrote one of the first English calculus texts. Colin Maclaurin in Scotland wrote another one that was very important. Maria Agnesi in Italy wrote one that was very popular, and probably the most popular of all of these and the most influential in the end was Euler's. uh, thing, and this is where he kind of expresses the modern idea of functions and for example, lifting up trig functions as other functions to work with. Maclaurin publishes the first systematic exposition of Newtonian calculus. Now, at this point, there are various different ways people are looking at calculus in terms of how they describe it and explain it and explain why it works and the language involved. So Newton referred to differential calculus with fluxions. Leibniz was referring to infinitesimals. D'Alembert based his calculus on limits, an early version of a limit concept. And Lagrange tried to base everything on a power series approach. So sort of some different approaches, different notations. But all of these things came under some criticism. Uh, for example, George Berkeley talked about fluxions and infinitesimals and had a criticism of them because he was saying, hey, look, guys, you're treating some of these values some of the times as zero and sometimes as not zero. And, is it zero or is it not zero? And one thing, one turn of phrase that he used I thought was pretty cool. He said, talking about ghosts of departed quantities. And basically he was saying, look, calculus is not really uh, rigorous in the way you've described it. You don't really have a good proof of it. And so that's one of the reasons why, for example, Maclaurin published his textbook is trying to explain why um, um, the calculus worked. And he actually used uh, techniques of the ancient Greeks. So he used Greek geometry and the uh, some of the different techniques that they used to try to go ahead and explain what was going on there. But the idea of trying to shore up these things, these ideas, and make them more rigorous, these addressing these complaints helped lead to the rigor that was going to come in the following century, in the 19th century, the 1800s. I want to lift up one specific problem that came up fairly early on in the century, maybe even at the very end of the last century, but it's talking about the brachistochrone problem, and that's a curve of quickest descent. Okay, so let me see if I can kind of show you with this GeoGebra thing what we're talking about. So let's see if we can open this up. Yeah, let's do that. Okay. So if we look here, we can say, what if you had a little ball going down, say, a straight path, a linear path? Well, that's certainly the shortest distance from A to B, but will that be the fastest that will roll? Okay, assuming all these are basically identically sized balls, will they roll there? Or maybe there's a different way. Maybe you can go by parabola. So this purple one is parabola. You can actually adjust it all the way from a line there to some different parabolas. This is another family of parabolas that you can look at there. This one here is a arc of a circle. And this one here is actually the right answer. We'll talk about what it is in just a minute. So you can see the red one is going to get there first. Actually, the line was the slowest of those particular ones. And I can adjust these parabolas here and try to see or adjust this circle, see if I can make it a little bit, better or worse. But it turns out no matter how I adjust those, it's that red one that's going to get there first. That is the curve that they were looking for. So the question is, well, what would be the equation for that curve? What kind of function is that? And this was a problem that Johann Bernoulli proposed, and he sent it to some of the leading mathematicians of the time to see if they could come up with an answer. and then he published some of those answers and looked them over. Okay, well, he actually solved it himself, and it's a cool problem in and of itself. But what's also cool about it is in developing answers to this got them thinking about some other kinds of ways to apply calculus, and it led to other things. For example, Johann's solution got him thinking about different properties of families of curves, and eventually that line of thinking led toward partial differentiation. His older brother Jacob also solved that with a different method, and his method led to the ideas around his method led to this field called calculus of variations. Leibniz also solved it, and Johann sent the uh, problem to Newton, thinking that Newton had plagiarized Leibniz's work and that Newton wouldn't be able to solve it. But Newton gave a perfectly good solution, gaining a little respect for him from Bernoulli. But the curve itself is actually a cycloid. So you can kind of see here how it's traced out. You take a point on a curve, point on a circle, and then roll the circle down, and you can see the curve that it's tracing here. So starting here, you can see it being traced out. So this red here on the bottom would be the curve that would get you to the bottom here, from this point here at the origin to this point down here, the fastest. And that curve is the curve they were looking for. So it turns out to be a cycloid. Another thing that they did in the 18th century is not only worked on, just advancing the techniques of calculus to solve mathematical problems, but a lot of this was spurred on by seeing how nice calculus was as a tool for solving many practical problems, particularly in the physical sciences. So they were worked on astronomy and planetary motion. Of course, Kepler's stuff was in the previous century or so before that. But they were still able to use calculus to help explain what was going on there. Optics and light, heat transfer. Uh, the metric system also came about. That wasn't necessarily calculus, but that was another thing that actually came about in that system, in that time period, particularly from the French mathematicians of the Revolution. They even had a system where instead of a week of 7 days, they had a decaday of a system of 10 days. That one didn't catch on so much. They had a thing called grads where you broke a circle up into one, if it was a circle or a semicircle, but you broke it up into 100 pieces instead of, say, 180 for degrees. Neither one of those things really caught on as much, but the metric system for the rest of things like measuring uh, distance with the meter, volume with the liter, and so forth, those things have definitely caught on, and really pretty much America is just about the only country, the United States is pretty much the only country that doesn't use the metric system now. There's also work done in electricity, fluid dynamics, and all these things had mathematical applications of mathematics. In fact, a lot of the same scientists who were working on these things were also the top mathematicians of their time, Euler, Bernoulli's, etc. There were some important algebra things that happened in the 18th century. Starting with, there were some important algebra textbooks. Newton, as part of his job, was lecturing on algebra at the university there, and he collected his algebra notes. Actually, somebody else took them and compiled and published them in 1707, about 10 years worth of lecture notes that he put together. And it was published as a book called Arithmetica Universalis, or Universal Arithmetic. And that particular book was in publication for over a century with new editions coming out. And so that turned out to be pretty influential, especially in the English speaking countries. Maclaurin also wrote a treatise on algebra. It included things like an explanation of algorithms, for sure, but also included working with negative numbers, as a complete description of all the known techniques for solving polynomial equations, including those of degree 3 and 4, uh, Cramer's rule for solving systems of linear type. Before Cramer, um, actually, Seek Takakazu published Cramer's rule in 1680 in Japan, uh, and Cramer used the method in his textbook in 1750, which is where it gets the name. But it was known to folks, at least 70 years before that. Some folks, at least. And Euler wrote a very influential text, and among other things, Euler's textbook helped solidify and standardize our modern notation for many things. One important fact in algebra is the fundamental theorem of algebra. It says that every polynomial with real coefficients can be factored into linear and quadratic factors. Well, it's something that people had conjectured for quite a while, but work was done on proving it. Fermat and Gerard made progress on it in the previous century, but some people started to think, well, maybe it's not quite true. Actually, Leibniz thought he had came across a counterexample, but in fact it wasn't. Euler gave a proof, what he thought was a proof, but it was actually somewhat flawed. So finally it was proved right at the end of the century by a young Carl Gauss in his doctoral dissertation, which was written in 1799. Algebra, they continue to work on solving systems of linear equations. Lagrange worked on solving polynomial equations and attempted to solve polynomial equations of order 5 or larger, but we now know that was doomed to failure because that was proved to be impossible in the following century. We'll talk about that a little bit more in our next playlist. There were some number theory advancements. If we go back to the previous century, we've got Fermat's last theorem. X to the n plus y to the n equals z to the n has no integer solutions x, y, z for n greater than 2. Now, if n equals 2, of course, we have all kinds of solutions. They're called Pythagorean triples. For example, 3, 4, 5 works. But Fermat had written in a margin of a textbook or margin of a book that he was reading, he wrote this down, this supposedly Fermat's theorem. And he wrote, I have a remarkable proof. Well, no proof was ever found of his work, no record of his so-called proof. I think it's much more likely that when he started working on it later, he realized that there was a problem with the proof and never wrote it down. But at least at some point, he felt like he had a proof to that in general. Well, it turned out it took a long time for folks to come up with a proof of this, and chasing down this actually ended up creating ultimately a lot of different areas of mathematics. But some work was done on it in the 18th century. Euler was able to prove this for the case n equals 3. The more general proof was not until late in the 20th century. We'll talk about that a little bit in a later playlist as well. Euler also did some other things. He worked with integers modulo n, so you may be familiar with those from an abstract algebra class or maybe in a discrete math class. And Euler worked with quadratic residues. In geometry, there were some advances there. Clairaut wrote a book called The Elements of Geometry, and his approach was a little bit different, say, than Euclid's approach. It was a little less rigorous axiomatic fashion than Euclid. What he ended up doing was starting with measurement concepts. He would start by measuring things and show that you could get certain ideas from there. So it was a little bit more informal in some ways, but he ended up ultimately developing most of the theorems in the elements, but from a completely different way of looking at it. And speaking of the elements, Euclid had 5 postulates. The first 4 seemed rather obvious, universal kind of statements of the way the universe is put together. At least that's the way they thought of it at the time. But the 5th one was a little more complicated. It's equivalent to what we would now call a parallel postulate. And so for many, many years, centuries, folks had tried to prove the parallel postulate based on the others. Many attempts were made before the 18th century, but 2 particular mathematicians worked quite a bit on this and made some interesting advances. Lambert and Sakari tried to prove Euclid's 5th postulate. And both of them, especially Sakari, came very close to discovering a non-Euclidean geometry, what we call hyperbolic geometry. But they were all they could not, either one of them, quite make that last intellectual leap to say that there might be a completely different kind of geometry. So they never felt like Euclid's 5th postulate could be wrong uh, or not valid in a particular situation. They really couldn't make that intellectual jump. So it's kind of interesting. We'll talk more about hyperbolic geometry being discovered in the next century. But the way they basically approached it was basically trying to not assume the parallel postulate, making a construction, and somewhere from that getting something that was going to imply the parallel postulate. So they did it by looking at quadrilaterals. Lambert looked at a quadrilateral with 3 right angles, and he attempted to prove that the remaining angle had to be a right angle without using the parallel postulate. And a Sakari quadrilateral is a quadrilateral that's a right trapezoid where the bases are congruent. And he was successful in showing that the remaining angles had to be congruent. But then there were 3 possibilities. The remaining angles were acute, right, or obtuse. And he was able to eliminate the obtuse option. But then he proved a lot of things about the situation in general. And so these are actually results that are true in what we call neutral geometry, a geometry that's neutral with respect to the parallel postulate, doesn't necessarily have a parallel postulate. And he actually proved some of these results that would be true in, say, for example, in hyperbolic geometry, as well as Euclidean geometry. He was able to prove those without using the parallel postulate. But at the end, he couldn't quite make the leap. He almost was the first one to come up with a non-Euclidean geometry, but at the end, he basically more or less said, well, it's just the nature of lines that they must be like this. And so um, we have that. So here's a little bit more information about him. Giovanni Jos Sakari was born in 1667, died in 1733. He was Italian. He became a Jesuit in 1685. Took the orders with that holy order. Became a Jesuit priest in 1694. The Jesuits were definitely, especially of that time, were definitely interested in learning and higher education. And so here you get an example where we have a religious group that is supporting intellectual inquiry. And so for years he studied and taught at a couple of 2 or 3 different Jesuit colleges in Italy. He did some work on logic, and then the work that he did, basically this says Euclid Vindicated in 1733, was the work that he wrote on this. And this work was not really widely disseminated among folks, so not a lot of people had read it. That's kind of unfortunate because had it been read by a lot of top-rate mathematicians, maybe somebody would have come up with non-Euclidean geometry a little bit sooner. It was not really rediscovered for about 150 years. Beltrami, I believe, then eventually found this work and uh, started, talking about what was in it and so forth. Another thing that started in the 18th century with Euler was the beginnings of graph theory. And it came from a particular little problem called the Königsberg Bridge problem. We have 7 bridges connecting 3 land areas up here. So there's a river going through here, and it kind of forks and goes around this island, and then it forks down here. So you have, I'm not sure which direction it's flowing, but it's all together. We've got these different 1, 2, 3, 4 land masses, and then the water. And if you look, there are 1, 2, 3, 4, 5, 6, 7 bridges. So here's sort of a simplified version of the picture down here. And people like to go for walks and walk across these bridges. And somebody said, what if I could go over all of the bridges just one time, and come back to where I started from? Is that is that possible? They kept trying to trace out different paths to see if one of them would work, with no luck. And so somebody asked Euler this problem, and so he said, well, you can replace this landmass with this point A, this landmass C with this point D and B for the other landmasses. Those were called, nowadays we would call those vertices, and the bridges that connect those landmasses would be these curves here, which we call edges. So we have vertices and edges, and so this thing you see here, B, is a graph that represents this or this up here, the actual reality of the situation. So the question now becomes, can we go from one vertex to the other following a path and keep going along this until we get all the paths covered and end back where we started? Well, the answer, maybe you want to pause this video here and see if you can come up with an answer for that. Okay, well, maybe you're back if you thought about it, but hopefully you found out something interesting. Let's just look at this vertex D. There are 3 paths out of it. Now, if you come in this path, you have to go out one of these other 2. And then, so let's say if you start there, D, you have to go out one path, then you could come in another, but then you'd have to go out the other one. You cannot start and end at that cannot be a starting place. Okay, well, it could be a starting place, but it can't be a start and an ending place. Okay. All right, well, what about C? Same thing. There's 3 coming out of there. B's got 3 coming out of there. There's 5 coming out of A. So these are all odd vertices. Every single one of these planes would have to be either a start or a finish. There's none of them could be both a start and a finish. So we see it's not possible to do that. So that's such a path, if it were to exist, is now known as an Euler circuit. Or more generally, if you just went through there and every edge once without repeating any edges, you can repeat vertices, but without repeating edges, that would be an Euler path. And we see that it has something to do with even and odd vertices. And this is considered the start of graph theory. We now use graph theory to talk about lots of different things. So you might have a class in graph theory. You might have a class might be included with combinatorics in a class called combinatorics or discrete math, perhaps. Now, another thing that's developing along at this time is probability and statistics. Now, if you remember, probability and statistics, particularly probability, was built on the earlier work of Pascal, Fermat, and I have a hard time pronouncing his name. I think it's Christian Huygens. But anyway, these guys, if you remember, Pascal and Fermat had the exchange of letters that kind of got probability started. Huygens had the first probability textbook, but that was all from the previous century. So a lot of what they were studying was games and gambling, games of chance. These things were continued to be studied in the 18th century, but to that we also added some further studies of annuity and insurance. Jacob Bernoulli had the law of large numbers. There's something called Bernoulli distribution or Bernoulli trials in probability, named after him. Uh, they also started to use statistical empirical probability. That is basically doing a simulation where you use statistics from your sample to determine what you think the probabilities are. Also, Pascal's triangle and was used, and along with combinatorics to help count up probability, different sizes, and were even some early uses of statistical inference. So there were some probability and statistics advances there. Well, let me lift up a few mathematicians that worked in this area. Abraham de Boive, born in 1667, died 1754 in France. He moved to England in 1688 to avoid religious persecution following a period where he was imprisoned. He became friends with Haley and Newton while he was there, and he made his living as a tutor. He developed analytic geometry and probability of theory. The Doctrine of Chances was a book about probability that he wrote in 1718, and there were later expanded and updated editions in 1738 and 1756. One of the things that he had in there was the approximation of a binomial distribution, which turned out to be an important thing there. He was able to know Stirling's formula before Stirling did. And the other thing that his name is most associated with is de Moivre's formula, and it's a formula for the expansion of cosine of the x plus I times sine of x to the n power. And another interesting thing is he predicted the day of his death, and he noticed that he was sleeping 15 minutes longer each day, and he extrapolated that out until when he would be sleeping 24 hours a day and said, well, that must be the day that I die. And sure enough, he was right. A couple of other important names in statistics and probability are Thomas Bayes. He was English. He was born in 1702, died 1761. He was a nonconformist minister. He taught at Edinburgh University, and he published a book in 1764 called An Essay Towards Solving a Problem in the Doctrine of Chances, and where he outlaid his ideas about statistics and probability, and actually probability, and he worked with conditional probability, among other things. And we've already mentioned in an earlier video in this playlist about Laplace. Laplace there, just to remind you, was from 1749 to 1827, and is a French mathematician from the later part of the 18th century, early part of the 19th century. And he also did some work on statistical inference. He proved many basic results in probability theory, and he had a textbook that was very important in probability. So that concludes our work on this unit, this playlist, and we'll pick up the next century, what happened in our next playlist.